Guys, we're going to get started on today's lesson. And today's lesson is going to be talking about, let me slide this down a little bit, empirical and molecular formulas. And we've talked about those briefly before. So let me just reiterate again what those are. An empirical formula is a compound that the smallest whole number ratio of the element of the substances, where a molecular compound or molecular formula is the actual numbers. So here's an example in this box here. So if we had water is H2O, that would be its empirical and also its molecular. And what we're talking about here is we're looking at these subscripts. And this subscript is a 2-to-1 and a 2-to-1. Okay? So when we start looking, though, at hydrogen peroxide, this is actually what hydrogen peroxide is. Okay? It is H2O2, and so if you look at it, it really has a 2-to-2 ratio. But we do know that that simplifies down to a 1-to-1, which is the empirical formula. Okay? Mercury bromide, empirical is 1-to-1, where its molecular is a 2-to-1, or sorry, 2-to-2. Okay? Some of them have the same. Okay, CH3 methane or CH4 that has the same. It's empirical and its molecular is the same. Methane, this would be a ratio of 2-to-5, where this one's a ratio of 4-to-10. Okay, but again, this would be the simplest whole number ratio as defined in your definition up here. Smallest whole number ratio. Okay, where the molecular is what's actually in the compound. Okay. So in other words, if you see methane, you're actually going to see it with 4 carbons and 10 hydrogens. Okay, so that's the difference between empirical and molecular. So here's some examples down here on the bottom of 55, and it wants you to write the empirical formula. And so basically it's like fractions. We're going to try to reduce this down. So 6 and 6, those will reduce by 6. And so the empirical would be just CH. 2 and 2, that would both reduce. So both of those actually have the same empirical. Okay, this one's 6, 12, and 6, so they'll all reduce by 6. So that would be C1, we wouldn't write it there, H2O1. Okay, see how we write that? C4, H10 would reduce both by 2, so it would be 2 and 5. P4O10 would be P2O5. Okay, so what we're going to do, I'm going to show you today is actually how to do the mathematical calculations to find the empirical formulas. That's what we're going to be doing today. Okay, and then once you find them empirical, the molecular is just a multiple of that. Okay, so let's just go ahead and get started here. Okay, so I'm actually at the top of page 60 is where I'm going to be working. And for some of these, you might actually need a piece of paper because they do require some work on them. Okay, so let's just show you what you do. Basically, what we're looking at when we're looking at, okay, so when we're looking again at empirical, we're looking at a ratio of the two compounds to each other. So in this case, we're looking for magnesium and oxygen, MgO, and we're wanting to know what is this ratio here? What is the ratio of X to Y? And when we talk about ratio, what we're talking about is mole ratio. Mole ratio, and I mentioned that the other day, I think, but if not, we'll talk more about it. But it wants to know moles to moles, basically, is what we're talking about. So in order to do that, we must do a conversion from grams to moles for these two. So that's all we're going to do is a gram to mole conversion. So let me show you how it goes. We start off with 4.04 grams of magnesium, and we're changing it to moles. So 1 mole of magnesium is how many grams of magnesium. And so we talked about this, and you worked some problems yesterday on how to go from grams to moles. So we go to the periodic table, and we find magnesium, and it's 24.31. Okay, so our grams of magnesiums will cancel out, and we're left with moles of magnesium. And so now we just need to do a calculation. So let me just get my calculator out here real quick. And I have 4.04, so you guys can get yours out and get it decided on. Okay, so when I divide it, I get 0.16618. Now I only have 3 digits. Okay, 3 digits there, 3 digits there. So 1.6 or 1.166, the next one number comes up as a 1. So that's going to be all I need. And so that is that many moles of magnesium. Okay. Now we're going to do the same thing with oxygen. 2.66 grams of oxygen. We're going to do a mole conversion. So 1 mole of oxygen, 2. And again, oxygen's mass is 16 grams for oxygen. And again, we're just going to do a division. 2.66 divided by 16. So again, that is 0.166 moles of magnesium. Now, normally, if you receive 2 different numbers here, so pay attention to what I'm saying. If you got 2 different numbers here, we always say divide by the smallest, okay? Now, in this case, they're the same number. So this one is pretty easy to see, but I'm going to go ahead and show you the steps. We would divide by the smallest. In this case, it's the same thing. And I know this seems redundant, but what I want to show you, it is a 1-to-1. Whoops, that was supposed to be oxygen. Okay, it is a 1-to-1 ratio. So this is MgO, and that would be your empirical formula. Okay, so I want to try another one here real quick for you. Make sure this is not too long of a video, but I want to show you one more. So this one, we're going to do iron oxide, and it's 22.24 grams of iron, 0.96 grams of oxygen. So again, we're just going to start off with 2.24 grams of iron. We're going to do a mole conversion, 1 mole of iron, and go to your table. So iron is, I'm sitting here with the lights off, so I can't see my periodic table, 55.85, there we go. 55.85 grams is what iron is, okay? Those units cancel, so I'm left with moles of iron. Now let's do a division. And again, I have 3 digits on each one of those. So this is going to be 0.0401. 0.0401. Almost didn't leave enough space there. Normally I wouldn't put my label on there, but okay, so until I was done. So let's go ahead and do the next one, 0.96, and this is grams of oxygen. So it's going to look just like the one up above. Okay, so this is why you really need to know how to do a gram to mole conversion. I'm going to go ahead and divide this out, and I get 0.06. Now, this one doesn't have any more decimals, but I do need 3. Whoops, actually, I only need 2. I messed up on that, so that should just be 40. Let's get rid of the 1. Pretend that's not there. So I need 1 more. There we go. Moles of oxygen. Okay, so there's my 2 moles. Now, the next step again is to divide by the smallest. Okay, so 0.04 is smaller than 0.06. So I'm going to take 0.040 and divide it by 0.400. That one's going to be a 1. Okay, I'm going to do the same thing here with oxygen, and I'm scooting it up because I've got my thing here. So 0.060, this time divide it by 0.040, and let's see what we get. So 0.06 really is what we have divided by 0.04, and it's 1.5. Now, there are some rules to tell you about. If the number here divides out, and it's pretty close to a whole number, like if it was in the 0.8s, 0.9s, I'd just go ahead and round it up to the next number. If it is 0.5 though, that's considered right in the middle and we really don't know what to do with it. So what we're going to actually end up doing is doubling it, because this is 0.5. So if I double it, I get a whole number, right? Everybody see what I did there? And it's because this is a 0.5. So when you have a 0.5, you double both numbers, okay? So what that means then in terms of this is that my iron is a 2 and my oxygen is a 3. And there would be my iron oxide. Now, there are times that if you have like a 1.3 or a 1.3 repeating, you happen to really get it and you think, hey, I really think this is a 1.3 repeating, then they might multiply it by a 3. Or if you get like a 1.6 repeating, that one you don't see as often, you might also multiply by 3 because they're the thirds. But it's very common to have a 1.5. Okay, that's pretty common. Okay. Now, I don't want to take up too much time, but I just want to start this next one. When you see percents, okay, we think of it as per 100. And so all we do when there's a percent is we just go ahead and change that value to its decimal value. So this would be 0.75 carbon. And then this would be 0.250 of hydrogen. And then again, we're going to do the same gram to mole conversions. Okay. So that is what you're going to be working on. And there's quite a few here that we're going to do. And there's several that we'll talk about, like the hydrate one. It's a little different because you have to do some adding and subtracting. But if they tell you what your grams or your percent of the elements are that make up the compound, you just do a gram to mole conversion and then do a ratio to find your subscripts. Okay. So hopefully that makes sense to you, and we'll be doing more.